Let us continue our discussion on 2D NMR. We looked at the simplest 2D NMR experiment in the last class, that was 2D COSY, where we correlate two hydrogen chemical shifts which are J coupled to each other, but only by 2 bonds or 3 bonds. It is very difficult, as I said, to connect hydrogens which are 3, 4 or 5 bonds away, because there is no direct J coupling between them. To overcome that problem, there is a new experiment or a subsequent experiments was developed known as 2D TOCSY, which stands for total correlation spectroscopy, as shown here. So, this is an abbreviation for this word, total correlation spectroscopy. So, let us see how this works and what is the additional information we can get over a simple 2D COSY. So, this is the pulse sequence of the 2D TOCSY. Typically, this is an NMR, this is how we analyze NMR experiments. What we do is we first look at the pulse sequence, how is the sequence of the pulses applied in a given NMR experiment, and once you practice understanding these type of pictures, you will get used to basically immediately understanding how the magnetization is flowing in this pulse sequence. So, we call it the flow of magnetization, and this is something as an experienced NMR person can immediately look at this diagram and figure out what is happening. At this stage, I would not expect you to obviously understand fully how this works, pulse sequence, but the basic ideas one should have a feel of, that is, one is they apply an RF pulse. The first pulse is always an excitation pulse in an NMR experiment, and then you evolve the magnetization. Now, during this evolution period, again similar to what we saw, there is a transfer we consider in the COSY experiment, but in a TOCSY we do not look at it as that. What we do is we assume there is no coupling. Let us not worry about any transfer here. Let us say that there is only a chemical shift evolution. So, chemical shift evolution happens during this period, and as soon after some time, again do not take this FID as literally the way that is shown here. We do not wait till it is over. It is, as I said, in a 2D NMR experiment, we always acquire one point and the entire experiment is repeated. So, we allow it to go for some duration here, and after that this block is applied. Now, what is this block? This block actually is a collection of RF pulses. This consists of 180 degree pulses typically. We will not go into detail of what is inside this box. Right now you can think of it as a black box. A box, basically what it is doing? It is doing is called isotropic mixing, meaning whatever magnetization comes here, it is now mixed with all other magnetization, and the output is of this here is the magnetization from A actually lands up all the way in a far away proton. So, if you recall in 2D COSY, we said that magnetization does not go beyond 3 bonds. So, we are looking only at 3 bond couplings, 3 bond transfer, whereas here we can actually go up to 5 bonds, 6 bonds, 7 bonds away, depending on the, of course, the coupling strength and how long we apply this block. But that magnetization actually goes from all the way from one proton to a far away proton, because of something which we do in this block. And this block actually, if you see, it is a weak RF radiation and it is applied for 60 to 80 milliseconds. So, this is a mixing time. So, this is a thing which you should keep in mind. A typical TOCSY mixing time, that is the time we apply this RF pulses or isotropic mixing block, is about 60 to 80 milliseconds. One should not apply this for a very long time, because that will start heating the sample and the sample may actually get destroyed or degraded. So, this is an important practical aspect which you have to keep in mind. And once this magnetization has been transferred from A, we will see that also in a diagrammatically shortly, has been transferred from A all the way up to a far away proton. All those protons now start evolving during T2. And therefore, what has happened is we have correlated, we are basically by transferring magnetization from one proton to another proton far away, we have correlated their chemical shifts. So, let us look at it little bit more in detail. So, this is shown as spin A. So, spin A is excited by a 90 degree pulse. It evolves by its chemical shift omega A T1. As I said, we ignore the J coupling during this part, which we did not in the 2D COSY. In 2D COSY, in fact, we needed that J coupling, but here we will ignore that, because for us we already have this which will do the 2D transfer or isotropic transfer. So, now we apply, so what happens is this cosine, the spin which is magnetization on A is transferred to B, C, D and so on as far as possible by this isotropic mixing. But what is the condition, how long can it be transferred? It depends on now the coupling between A to B, B to C, C to D and so on. So, what we are trying to do in a TOCSY experiment is we are trying to exploit that there are couplings between A to B, and then from B to C there is a coupling, and from C to D there is a coupling meaning J or dipolar coupling, and because of that coupling we are trying to transfer A to all the way to a far away spin. So, if there is a break, that means suppose C and D are not coupled, then we can't go from A to D, because that break will stop at C. So, our magnetization will not be able to transfer all the way up to D or E or F or whatever number of spins here, because we encounter a break. So, we will see that in say a few examples that A to a long chain can be transferred, but if there is a break it does not work. So, as long as A to B is coupled, B to C is coupled and so on, it can be transferred. So, once the spins the magnetization from A is transferred to B, C, D and so on, this isotropic mixing block is over, and then you start detecting whatever has been transferred. So, that transfer is now detected. So, B will evolve with its frequency, C will evolve with its frequency, D will evolve with its frequency and so on. But each time each of these evolutions are actually connected to this now, because they are coming from that only, they have come from A only. So, that means we are correlating A to B because of this connection, and we also correlate A to C, we correlate A to D and A to E and so on. So, you see we form a chemical shift correlation between A and D and C and so on just by using this TOCSY concept. So, this is a very useful experiment because it gives us a long range transfer information which we will not get from a simple COSY. So, correlates all homonuclear shifts that are coupled through J coupling. So, this is an important point here in a TOCSY, that we correlate all homonuclear chemical shifts that are coupled together, meaning there should not be any break. The A, B, C, D, E are 5 hydrogens, A should be coupled to B, B to C, C to D and D to E. It can't be that if A to B is coupled, but there is no coupling B to C, then I can't go from A to E because of the break. And now, before we look at the actual spectrum, the diagonal peaks which we see in TOCSY is similar to a COSY, that is the diagonal peak is just a 1D spectrum. There is no difference between the diagonal peak of a COSY and a TOCSY. So, diagonal peak are same, whereas the cross peaks are completely different types. Of course, the 2-3 bond here, suppose A to B is 3 bond, that interaction also will be there in COSY. So, as far as near neighbors are concerned, meaning 2 hydrogens which are coupled to each other, they are only 3 bonds away, they will be the similar, they will have the similar correlation as in a COSY. But those which are far away, that correlation is not there in COSY, but will appear in the 2D TOCSY spectrum. So, let us again look at the same molecule which we saw earlier. So, the propyl chloride, you can see here I have this hydrogen which is okay, this label has shifted, this hydrogen is 1, this proton is 2, this proton is 3. Now, in a 1D spectrum, again similar to what I said in the previous class, we will just see 3 lines, and again I am telling ignore the J coupling right now, we are only concerned with the chemical shifts. So, we are looking at chemical shift correlation. So, we will not worry about the finer details of J coupling, it does not matter for us in the analysis of 2D or even for that matter in 3D. So, we need J coupling for transfer, no doubt about it, but we do not need J coupling to appear in the spectrum, or we do not need to see them very in a more detail. So, we will ignore that. So, this is a 1D spectrum. So, now if I draw a 2D spectrum, how will I get, what kind of pattern will I get in a 2D TOCSY? So, this is a diagonal peak which is similar to a 1D spectrum and similar to what we saw in the COSY. So, there is absolutely no difference as far as diagonal peak is concerned between a TOCSY and a COSY. But let us analyze the cross peaks now more carefully. So, you can see here between proton 1 and 2 there is a 3 bond coupling, and therefore, because of this 2 coupling because of this 2 protons, you will see a cross peak. This is similar to COSY. There was no difference between this and a COSY, the same thing is drawn here again, and you can see here also it is the same to COSY. So, there is actually no difference till here at this point, but now in a COSY we could not see a coupling between proton 1 and 3 because they was far away, but now you can see here if there is a intermediate 2 is present here. So, in this molecule, so if 1 is coupled to 2 and 2 is coupled to 3, so in a TOCSY I can connect 1 to 3 via or through the coupling to 2. So, that is basically the advantage of TOCSY, that I am able to get a new cross peak between a proton and another proton, which otherwise will not be seen in a COSY spectrum, and that is basically because we are able to use this isotropic mixing concept to transfer magnetization from one spin to a far away spin, and this is something which you will not be seeing in any of this 2D experiment, COSY experiment. So, therefore, TOCSY was a very important development in NMR for assignment of molecules, because you see the entire molecule you can get in a spectrum. So, this is like suppose let us say I have a mixture of two molecules, and let us say I have one more molecule present here which I am not showing here now, but if there was present, that molecule would have again a connection between among its protons, but it will be different from this pattern because it will be different molecule. But by looking at this, you can see this is like a square grid. By looking at this grid like thing, I can get the full the details of chemical shift of one molecule which are connected to each other, and I will get the same details for another molecule where also I will get connections between the atoms of that molecule. So, by using TOCSY, one of the most important application in TOCSY is to identify what is called as a spin system. So, spin system is a word which very often is used in NMR in biomolecules, where spin system basically consists of a system or a set of spins which are coupled to each other by J coupling. So, there is no break here, all these three are belonging to one set of spins which are coupled, and we use the word spin system. But we will see one example where the same molecule. So, we have to keep in mind in this case one molecule is one spin system because all the protons are connected, but you can have in one molecule two different spin systems because of a break. So, we will see that shortly. So, this is what I was alluding to. We use the word spin system, which basically looks at the entire set of connected spins as one family meaning one set of spins. So, spin system is a set of nuclei that are J coupled to each other. Now, let us look at an example. This is a real spectrum of a molecule 3-heptanone, which we saw in the for COSY. So, here you can see that here we have 4 protons, but there is a break here. Break meaning there is a carbonyl here which is not allowing the coupling to go from 2 to proton 4 to 2, because you see that there is no proton here. So, for example, if I want to do a TOCSY connection between this proton which is labeled as 4 to this proton which is 2, I need to depend on one bond which is this carbon proton, 2 bond, 3 bond and another 4th bond to this proton. So, I need 4 bond J coupling if I want to correlate a TOCSY, see a correlation in a TOCSY spectrum between 2 and 4. So, as I said, that is not possible, we are not, there is no direct coupling. So, this basically breaks this whole molecule into 2 parts. In one part it is one spin system which is these 2 protons which are connected to coupled to each other by J coupling, and these set of 4 protons which are connected to each other by again J coupling. How? Because 3 is connected to 2 by J coupling, 2 is coupled to this 7 is coupled to 6, 6 is coupled to 5, 5 is coupled to 4. So, by this kind of chain of coupling, so this is the important term, coupling chain network, we are able to connect all these 4 through in a TOCSY experiment. So, you can see here you start from if you look at let us say 7 here. So, this is a diagonal peak which as I said is nothing but a 1D spectrum of the molecule. So, you start from 7, I can either go horizontal or I can go vertical, we can choose whichever way we want. So, let us go horizontal because it is labeled here. So, if I start from H7, I am seeing a correlation to H6 and this is a cross peak. Now, you can see there are some small multiple lines, and that is because of the J coupling multiplet, which as I said we will ignore, we will not bother about it, but in a 2D NMR they will show up because of the high resolution. Now, from H6 I am getting okay from H7 I am getting correlation to H5 as well, and that you can see here 7 to 5 will not come if I had a cozy spectrum. This happens only in a TOXI because of this intermediate coupling to 6. So, 7 to 6 is a pure TOXI effect, 7 to 5 is a pure TOXI effect that will not happen in a cozy. Now, you can see we are also getting from 7 to 4 because again because of this intermediate coupling between 7 and 6, 6 and 5 and 5 and 4, I am able to go all the way from correlation from 7 to 4. And now, if you look for each of these other spins, the same similar situation happens. 6 is coupled to 7, or this is this peak here, and then 6 is coupled to also 5, 6 is also coupled to 4. So, 6 is coupled to either side, on this side 7 and this side 5 and 4. Similarly, 5 is coupled to 6 and 5 is coupled to 6 and 7, 5 is also coupled to 4. So, all are coupled to each other. So, you see it is like a square, all with all. So, this is the typical pattern which you get in a TOXI spectrum, but you see now we are not able to get any coupling or any cross peak between 7 and 2 here all the way. So, that you see there is 2 here, this is here. If you draw a vertical line here, I am not seeing any peak close to 4 here, you see here. I am not seeing that because there is a break here because of this carbonyl, and therefore, I am not able to connect from 7 to 2, but 2 and 3, let us look at 2 and 3. So, 2 and 3 is not shown here, but 2 and 3 actually are connected to each other because they are J coupled to each other. So, this is like a simple 2 spins. So, this is one spin system consisting of 2 and 3. You can say this is one family or one set of spins, and this set of spins is another set which is coupled to each other in a family. So, this is one spin system and this is one spin system. So, there are 2 spin systems in the same molecule. So, therefore, one should be very careful and not assume that a spin system means one entire molecule. A spin system basically is a set of spins within a molecule which are coupled. So, in a given molecule you may have more than one spin system, more than one different spin system. But for us fortunately in biomolecules each amino acid is one spin system. So, this is the connections which are shown here. As I said, we have 2 spin systems in this molecule. So, in a biomolecule we do not have to worry because in a biomolecule there is no such breaks. So, the one amino acid, a given amino acid, whatever the one of the 20 amino acids naturally occurring, all of them form one spin system. In the sense each molecule is one full spin system. So, there is no such multiple spin system. So, this is a comparison now of a TOXI and a COSY for the same molecule. So, you can see there are many additional peaks which are appearing in TOXI and not there in that COSY, and this is something which we already saw. This is because of the concept that you have a far range coupling, the TOXI is possible to transfer all the way, whereas you can't do that in a COSY. In a COSY only they are restricted to 3 bond coupling. So, this is basically about 2D NMR of TOXI. We will move on to 2D nuclear Overhauser effect spectroscopy, and this is now a completely different type of transfer of magnetization from one spin to another, and this is a very important experiment in NMR. In fact, this is the experiment which actually resulted in biomolecular applications of NMR and which subsequently also resulted in the Nobel Prize for Professor Wuthrig. So, nuclear Overhauser effect or NOE is a very important effect in NMR which actually is used in routinely for not only small molecules in biomolecules, for every particular any other aspect as well. So, before we understand how nuclear Overhauser effect works, we have to look at, or the nuclear NOESY experiment works. Let us look at this concept of what is a NOE effect. So, NOE effect basically is an effect which is through space interaction. So, this effect happens because of through space interaction. Basically each proton, so if you recall the very first slide in this course, a very first few set of slides, we said that each nucleus is actually a dipole, magnetic dipole. So, each nucleus has a magnetic dipole moment. So, if you have 2 hydrogens in a molecule, they are also 2 dipoles. So, any 2 hydrogens or any 2 hydrogens you take, any hydrogen for that matter, any proton is a dipole, is a magnetic dipole, is a tiny magnet. So, therefore, any two protons now will interact with each other. They will interact, meaning they will couple to each other, they will have dipolar coupling between the two. This is just a natural phenomenon which is not in our control. It is just any two dipoles you bring close to each other, they will start interacting. So, now look at this molecule here, which we have been looking in the last few slides. So, here these two hydrogens or these are very close to each other in space. So, remember we are looking at space interaction now. So, we are not talking about through bond. So, they may be 3 bond away or 5 bond away, but in space, that is if you draw a 3-dimensional structure of this molecule in 3-dimensional space, they may come close to each other. So, when we say close, how close is considered as close? So, typically in a NOE experiment we say 5 to 6 angstroms is the distance which we can think of as close, meaning any two hydrogens which are within 5 to 6 angstroms or any two protons which are within 5 to angstroms are affected or by each other by dipolar coupling. So, therefore, now if I irradiate, that means I apply a signal only on this proton. This is, let us assume that we are able to do that. How we do that, we are not going to go into detail, but let us say I am able to do that. That irradiation, because it is now coupled to this hydrogen, it affects the magnetization of this as well. So, this is a pure it is a very simple logic, that if I have A and B two spins and if they talk to each other, if I disturb A, B is also disturbed. So, any two spins which are coupled to each other or any two atoms, if I disturb one atom and if there is a coupling between this 1 and 2, the second is also affected. So, therefore, this is also affected. Now, because this is affected, this is also affected, there is a chain reaction. So, basically NOE, initially 1D NOE which started in the very beginning worked like this, that you irradiate RF, you take an RF pulse, you irradiate on a particular selectively on one particular proton, the entire proton, the spin system, again remember the word spin system, all the atoms in the spin system protons which are close to each other, they will be affected. So, therefore, their signal in NMR spectrum is also affected. So, this is one of the earlier concept which started in NMR. So, this is this slurry, this is slightly, the arrow has got shifted, this is not chlorine, we are not talking about signal of chlorine, this arrow actually has to point to this hydrogen. So, this hydrogen to this hydrogen, this hydrogen to this hydrogen. So, the irradiation zone, as I mentioned, that is how far away should the proton be, two protons, so that they affect each other, is the 5 to 6 angstrom. But remember, this proton and this proton is not 5 or 6 angstrom, it is maybe more than that. But because A is connected to B and B is close to C, there is an effect on A to C, like a TOC. So, there is a long range effect just because there is a intermediate hydrogen which relays the carries the magnetization from A to B to C. So, this is we use the word spin diffusion. So, in NMR NOESY experiments, there is basically a very important concept that is called spin diffusion, which talks about this transfer of polarization or magnetization from one hydrogen to another hydrogen, because they are very close to each other. So, NOESY therefore is a very information, a very important experiment which gives us the information of the proximity between two atoms. So, example, let us say here these two hydrogens, we do not know what is the distance, let us say we do not know the distance, but if I disturb this hydrogen by irradiation and if it affects this hydrogen in the spectrum, immediately I can conclude that these two hydrogens are within 5 to 6 angstrom. So, this is basically the way we look at NOESY. It is very useful to telling us the proximity between two hydrogen atoms. So, it immediately tells us, yes, these two hydrogens are closer than 5 to 6 angstrom, and this is an information which we normally do not get from TOC and COSY. TOC and COSY are only telling us the chemical shift correlation between two hydrogens through bond experiment. But imagine now a structure, a very complicated molecule like a protein or a nucleic acids or any other complicated system, where there are not 3 atoms, but there are hundreds of atoms. So, imagine that for a time being. So, if I have hundreds of hydrogens or thousands of hydrogens, one hydrogen may come close to some hydrogen number 67 or 150 or 360, Now, that interaction will never happen through bond, because at 300 bonds away proton obviously cannot have any J coupling, but it may come close in space like this. So, this is proton number 1 and let us say this is proton number 300, which is really very far in through bond, but it has come in close through space because of the 3 dimensional structure property of the molecule. In that, if that happens, then the proton number 1 actually affects the proton number 300. If I irradiate proton number 1, proton number 300 is affected. So, you see I get a distance information, proximity. I am not getting exact distance value, but at least I know that they are within this distance range, and I can immediately conclude that the proton number 1 and proton number 300 is within 5 angstrom, but actually if you calculate through bond, they may be 300 bonds away or 310 bonds or 5 bonds away, which means they are really very far if you consider through bonds, but they are very close if you consider them through space. So, this is a very great advantage of a 2D NOESY experiment or a NOESY in general. There are different variants of NOESY experiments, a 1D NOESY, 2D NOESY, a transient NOESY, which we will see only 2D transient NOESY in this course, because that is the NOESY experiment which is very useful for analyzing the structures of biomolecules. And again one word before we end this class today is that it is basically the dipolar interaction. So, you have to remember TOCSY and COSY were through bond interactions, and NOESY and ROSY, which also will come soon. These two experiments rely on through space interactions, and together they constitute the very important set of experiments which can be further extended to heteronuclear NMR. So, we can have heteronuclear NOE, heteronuclear COSY, heteronuclear TOCSY, which will look in the heteronuclear part, and all these together are very useful for biomolecular studies. So, we will take up the full details of how a 2D NOESY experiment. We will specifically look at only transient NOESY. We will not look at a steady state NOE in this course, because that is a very old technique which is not used anymore in biomolecules. So, we will look at the 2D transient NOESY experiment in the next class.